Hello, my name is Nastin Yanofsky, and so this video is a organizational video. We're going to start talking what I plan on doing. So I wrote this book called Monoidal Category Theory, Unifying Concepts in Mathematics, Physics, and Computing. Came out by MIT Press, came out in November. And what I'd like to do is I'd like to make a series of lectures which goes through the book section by section and teaches the stuff as we're doing. Now, it teaches the stuff that's in those sections. Now, I don't want to read the book to you, and I don't want to be your lecturer to the book, but what I do want to do is I want to go through every single section, show what concepts are there, show the major ideas, do some exercises, do some things, and to show you. Now, obviously, it's a thick book, and I can't do every single word, and I can't get into every single technical detail. You'll have to read the book on your own, but this is what I'm intending to do. So it should be like 45 to 50 videos each section. Some sections are very small, so they'll take 15 minutes or something. Some sections will take an hour. Some sections will take 2 hours. Sometimes we'll have to do 2 different videos for one section. We have mini courses that go on for pages and pages, and sometimes you want to get into a lot of those details. So that's what we're planning on. That's what I'm planning on doing in this series of lectures. I'm going to come out with a few, and then it'll take about a month or 2 or 3 to get through to all of them. But the book is available and worthy of doing. So let's start off talking a little bit about category theory, and let me make a sale for category theory. Category theory was a branch of mathematics that extended, and it's now part of computer science. It's now part of physics, and it's become somewhat of the lingua franca of the sciences. It's this language which is very concise, but you can express a lot of different ideas with this language, and so I want to present this in a way that doesn't assume that you're a mathematician. I'm not assuming you're a mathematician. I'm not assuming you're a physicist. I'm not assuming you're a computer scientist. I'm not even assuming you're in college. It's just a language that can describe a lot of phenomenon in a lot of different areas. And it's nowadays you can find people talking about category theory in neuroscience, in philosophy, in lots of different areas, and in chemistry and biology, etc. So it's a language, and you'll see why, that can just talk about different phenomenon in different things in different areas, but it's a single language. And in that sense, it's somewhat unifying, because this one language can talk about all these different things. Hence the subtitle of the book, A Unifying Language. So it's not just a nice, simple language, but because you can talk about many different things, you get that. We'll talk about this some more in a second. Okay? So it's a lot in the news. And the whole field is a beautiful field with lots of examples in history and the most deepest ideas and thoughts. Okay, and I'm hoping that this video will help those who want to learn it easier and better. Okay, at the end we should have about 45 videos, and each video is a different topic in category theory, or in an application of category theory, etc., etc. So I'd like to start off this video just first of all to give you a structure of the book, and then tell you a little bit about what categories are. Don't get into details, and a little bit about some of the structures that we're going to meet and talk about, and the language that we're going to talk about then. Okay, so the structure of the book is as follows. There is 10 chapters to the book. Chapters 1 through 4 is an introduction to category theory. Okay, and usually a one-semester course would cover those 4 chapters. But it's not my intention. What I want people to do is skip through some of that and go to the more interesting things. And so that's what. So let's just go through it. Chapter 1, which is what with this section, chapter 1, which is about an introduction. But we introduce things starting with with sets. We talk about sets and functions between sets, and we'll see that that has a lot of the structure that categories need. So we're going to spend a lot of time talking about different sets and how you make a product between two sets and what's functions between two sets, and we're going to find a lot of different ideas at that. Chapter 2 gives you the basic definition of what a category is, and then the beginning of it is just a ton of examples of what a category is. Chapter 3 goes through the structure within a category. In other words, categories are not just collections of things, but they have structure in it, and we talk about that in lots of different ways. That's chapter 3. We talk about things called products and co-products and limits and co-limits and stuff like that. And then chapter 4 is where the real magic of category theory is all about, and that's where categories relate to each other. Okay, and that's the largest section of the beginning of the beginning of the book, and that's where most of the meat of the first 4 chapters are. Okay, and we'll get into that. So you're going to have concepts of categories, and you'll have one category and you'll have another category, and you want to see how they're related to each other. Just like sets, you can have 2 sets and you can have a function in between them, so too you can have functors, something called functors between 2 categories. We'll talk about that in a second. Okay, next. Chapter 5, 6, and 7 is about monoidal categories. Monoidal categories are special types of categories. They're categories with more structure. And so we go through that in those 3 chapters. And I'll talk about that a little bit later, getting into that. Okay? Okay, next, chapter 8, 9, and 10 are more advanced topics that an advanced student might want to be interested in. Okay, chapter 8 is called it's different ways of talking about structures. I've been using the word structure a lot. Okay, so algebraic structure, there's lots of different ways of discussing structure, and that's important because when we're talking about a unifying language, we're going to have lots of different types of structures that different things happen. I'm not being very specific of what I'm talking about, and that's the magic of category theory, because I can talk about a lot of different things using the language of category theory, so I don't want to get bogged into one thing. Okay, chapter 9 is advanced topics, and then one of the most beautiful parts of this book, I think, is at the end of every chapter there's something called a mini course, where we take the knowledge that we know from that point of view, and we go through an entire mini course of some topic in computers, math, physics, etc. Okay, and we present that topic with the category that we know. Okay, so there's about 13 mini courses in this book, which again has an entire explanation of an entire field just on the category theory that we learned from, just using the category theory that we just learned. Okay, in this field, we have something on duality theory, we have something on self-referential paradoxes, we have a mini course on quantum theory, we have a mini course on quantum computing, we have a mini course on knot theory, we have a mini course on linear algebra, 2 mini courses on linear algebra, we have a mini course on logic. The key point is all these different fields seem like, what the hell, how are we going to unify them? Well, that's the whole purpose of category theory. We're going to unify them, and we're going to see that they all have similar structure, etc., etc. So the last chapter is called chapter 10. The last chapter is chapter 10, and what that's about is 3 more mini courses where we go through other things that can be done. There's a lot more mini courses to do, but the size of the book requires that we stop at some point. The main point of this book and the main point of category theory book is that with the knowledge of category theory, you can pick up a lot of different fields and understand a lot of different things, because it gives you the basic structure of what you're talking about. And so if you get someone else who speaks that same language, they can explain it to you fairly quickly. Okay. Okay. So this book, there are a lot of great introduction to category theory books. This book is a little bit different than those, and one of the things I stress in this is lots of examples, okay? And you see examples with the mini courses, and you'll see examples from all over. But not only math examples, but computer science examples, physics examples, things like that. We're always going to see lots of examples. I was thinking of titling this book called Category Theory by Example. I really like that, but anyways, the book is called Monoidal Category Theory, but again, it starts off talking about regular category theory, then monoidal category theory, then advanced topics. Okay, so, but we're going to stress examples. We're going to see, every time we see an idea, we're going to stress it. Okay, so before I start talking about what categories are in particular, I want to just say if there's any comments or criticisms or something, you can email me if you have a way of me improving these lectures. I'm all open, and I like to hear from people. So feel free, send me an email. You just type in my name, you'll get my webpage, send me an email, and I'll respond usually. Okay, so I want to talk about I want to talk about a little bit of the history of category theory, and what I said was it's a unifying language, and I want to explain to you what I mean by that. Category theory was started in the 40s, okay, and the idea was as follows. There were a lot of geometric type of things that people were dealing with. And I don't want to go into what they are because I'm not interested. We're not talking about those things now. But there were a lot of geometric type of things. And so these things were called topological spaces. Okay, and again, we're not interested in what they are. Manifolds, okay, bundles, pointed spaces, lots of different types of things that were here, and these are all geometric type of ideas, geometric type of things, okay? And then there was something called algebraic type of ideas, okay? And here we had groups, rings, vector spaces, abelian groups, lots of different things, okay? And what was happening in an area called algebraic topology is people were basically assigning to these types of objects these types of things, okay? They were somehow describing the geometric things using algebraic structures. They were describing the geometric structures using algebraic structures. And the way they were doing this should be let you think of what a function is, and it's a type of function, but these functions had funny names, and again, we're not interested in it, but they were called homology, cohomology, homotopy. These were K-theory. Oh, that's a little early, but okay. They had funny names, and each one of these different functions was taking a geometric object and assigning it an algebraic object. Okay? The main point, and the reason why I'm saying this is because what you should get out of this is that if you want to talk about both of these types of things, both geometric things and algebraic things, you need a new language, a language that's not geometric centered, and a language that's not algebraic centered. Okay, and the two founders of category theory did this. Okay, one was named Saunders MacLean, and one was named Sammy Eilenberg. And in the 40s, they said, okay, you know what we have here? We have some interesting things. We have objects of a certain type here, we have things of a certain type here, and we're relating them. And so they came up with the notion of categories. Okay? Main point is, by this new language called category theory, by not being about geometric objects and by not being algebraic objects, but being about nothing, they can encompass talking about both of these things. Okay, so that was the goal. So there's two notions of a unifying language that's going to go throughout this book and which is central to all of category theory. One, category theory is a unifying language because we can use one language to talk about many different phenomena. That's one thing. The other thing, and that's what I stressed earlier, the other unifying aspect of category theory is that it's about relating objects of one type to objects of the other type. And that is a unifying thing. So what we're going to do throughout the book, especially after chapter 4, is we're going to have some type of idea or structure over here. We're going to have some type of idea or structure over here, and we're going to describe a way of relating these types of structures and showing that this structure has similarities with that structure. Okay? And if they have similarities, what can we say about this structure? What can we say about this structure? And how much could this relationship, how much of it does it preserve? Okay? But that's a unifying theory. That's a unifying idea. Namely, if this is one thing and this is another thing, and we see that they're related by some type of map or function, then that's unifying in that sense. Okay, great. So that's motivation of what category theory is all about and why it's important and why it works so well. Okay, and it does work amazingly. Okay, so what is a category? Okay, and the idea is as follows. A category is a collection of certain types of structures, certain types of things. I would say it's a set of things. Okay? Okay, but a set of things that are the same type of things. Okay, same type of things. So you might have, well, I don't want to say what you already have, but so when we talk about set, you can make a set of this and a set of that and a set of that. Well, these are three things that are here, but that's not the important thing. You can have the set of students. You can have the set of American citizens. You can have the set of atoms in a room, whatever. These are collections of one type of thing. So a category is a collection of one type of thing. However, they also contain relationships within these types of things. So there's morphisms within a category. There are morphisms. These little arrows are called morphisms or maps or arrows between objects. Okay? And we'll get into nitty-gritty details of what these are very soon, but the main point is as follows. These morphisms, or these maps, call them what you will, there could be more from one, there could be some loops like that. Okay? They have like that. Okay? Now you might say, if you know about this thing, you say, oh, this is a group. This is a graph. You have little dots, objects, and morphisms. No, this has more structure than a graph in the following sense. Okay? And this is very important. If you have a map from here to here, and you have a map from here to here, then you can compose the maps. And by that I mean there's automatically a map from here to here, and we're going to call it F compose G. Okay, so let's focus our attention now. Let's go inside a category. You might have an object, we'll call it A. You might have another object, we'll call it B. You might have another object, we'll call it C. And you might have a map from A to B. And we write it like this. F goes from A to B. Okay, you might have another map from B to C. And we'll call that G. And we say G goes from B to C. So here's two different ways of writing it. Okay? But a category, part of the structure of a category is not only do you have these maps, but we insist that you can compose these maps. Okay? And you get another map. And this other map goes from, you follow the arrows. It goes from A to B and then from B to C. And we write it a little bit funny, F composed G. So let's write it over here. F backwards, G goes from A to C. Okay? So just like you could take two numbers, X and Y, and you can add them together, just like you could take two numbers, and subtract them, etc. So those are operations on numbers. So too we have an operation on maps in a category. If you have a map like this, and you have a map like this, then you're going to have a map like this. Okay, so that's basically the definition of what a category is. Okay, so it's a collection of things and maps between these things. You might think of them, it's a collection of structures and structure-preserving maps between them. Okay, now I want to explain to you why people find category theory to be difficult, and then I'll show you why it's not difficult in this book, and that's very, very nice. Because once you have a category, guess what you do? You talk about another category. And this other category also has maps between things and composition maps, etc., etc. Okay, so you might call this category A, and we might call this category B. Okay? Okay, great. Now, this category is a whole world to itself, and it has structure, and we have to talk about it. And this category is a whole world unto itself, and it has structure, and et cetera, et cetera. But now, what's interesting is you have functors, which is a word similar to functions. Let's remind ourselves, if you have a set and you have another set, you have a function between sets. Okay, so too here, we're going to have a category, and we're going to have another category, we're going to have functors between them. Okay, and so we're going to call this functor capital F. I'm not telling you what a functor is. I'm not telling you what a functor is now. I will tell it to you in chapter 4. But you might have two functors. Okay, that's relating this object, this category, to these categories. Okay, so the reason why category theory is considered sometimes hard is because you have to keep in track of where you're talking about. Are you inside the category and talking about these maps, or are you outside of the category talking about these maps? So this is a little bit sometimes confusing. It won't be confusing in a second, but let me just tell you further. Okay. Furthermore, you could have maps between functors. Okay, so not only do you have categories and functors between these categories, you can even have types of functors. Well, they're not really functors, I'll give you the name in a second, from one functor to another. These are called natural transformations. Okay, sometimes they're written with a Greek letter. Alpha, beta, gamma, something like that. Okay, so you basically have 3 levels of structure here. You have categories, you have functors between categories, and then you have natural transformations. People don't like that. That's a little bit complicated to think about. Okay. Besides that, you also have within every category, you have structures here, and you have objects and morphisms between them. So you have to keep track of this. Now, that's why a lot of people get put off about learning category theory, because you have to keep all these different things in the mind. Let me tell you why we don't have to worry about this. Okay? Because what we deal with, okay, for the first 3 chapters is just categories. We don't mention the word functors. We don't mention the word natural transformation till later, till chapter 4. So we're going to get used to just talking about categories. And we're going to talk about categories here, and we're going to talk about lots of different examples of just categories. And we're going to spend the first 100, 150 pages just talking about categories. So that's a very pleasant thing. We're not going to use that word, I will not mention that word functor or natural transformation until we get to chapter 4. I'm just foreshadowing and showing you what will be and why it's important. But we have to get all our examples straight. And so that mind-blowing experience of being in 3 different dimensions at one time and worrying about what's going from what to what, you don't have to worry about that for a lot of videos. So that's an easy type of thing. Okay. Okay, so those are categories. Okay, Now, I would like to talk to you also about what's about chapter 5 and 6 and 7. And the idea is as follows. Not only do we have categories, but some of these categories have interesting structure within themselves. We saw they have maps in between them. But you can also have certain categories where you can do operations on the objects also. And I just talked about doing that. I said if you have a number x, you have a number y, you can do an operation on them. And you can do a lot of different operations on numbers. You can do x divided by y, etc., etc. Okay? So too, there are many times where you have a category where you can do operations on the objects in the category. You can multiply them or combine those operations. So you might have an object in the category, okay, and then you have another object in the category, and then you have an operation. And I'm not saying what the operation is. In each case, it will be a different thing. But the main point is you have this way of combining elements. So if you have a little element C and you have a little element X, you might be able to combine the elements, and I make this interesting symbol, C cross X. Okay? But these are not just sets, like sets of numbers. These are categories. And so we not only can combine objects, but we can also combine maps. Let me show you what I mean. Okay? We combine those arrows. So within a category, you might have a map from A to B, which we'll call F. And you might have a map from C to D, which we'll call G. Okay? Well, these special categories called monoidal categories, okay, you go further with them, and you can multiply the objects. So you can have an object A, okay, and that's called tensor C, and you can now multiply these objects too, B tensor D. Okay. Well, guess what? There's a map from here to here, and it's called F tensor G. Okay. So in these special categories called monoidal categories, you can not only multiply or combine objects, you can also multiply or combine morphisms. Now, let me tell you why that's interesting. Okay. First of all, we now have two ways of combining morphisms. For example, we can do A, B, and then C. Okay, and so we have F. We call this F. We call this G. We call this F. Compose G. That's one way. And the other way of talking about it is if you have like this, you can compose it. So with a tensor. So this we call composition. This we call tensor. Okay. The way to think of this is first do F and then do G. So first do F, then do G. So you might want to call this as well, regular processing. In computer science, you call this sequential processing. Sequential processing. What does that mean? Do one and then do the other. So that's called sequential processing. Okay? As opposed to this you might look at as this. Here's A tensor C, here's B tensor D, and you might say that this arrow from here to here is doing F tensor G. So here's F, here's G, and you're doing F tensor G. And the way to think of this is you're doing then from A to B you're doing F, and from C to D you're doing G. Yes, you're combining them, but you're doing them one at a time in that. Another way of talking about this is if this is sequential processing, this is parallel processing. Doing one thing at the same time as another thing. You're doing one process at the same time as you're doing another process. So let's go through this. Sequential processing is doing this one at a time and then another one. And parallel processing is doing both of them at the same time. Parallel. Okay? Okay. Now, monoidal categories was So let's go back up. Category theory was started in the mid-40s by Saunders, MacLean, and Sammy Eilenberg. In the 60s, a guy named Ben Abu and Sammy Eilenberg also, they formulated this notion of monoidal categories. Okay? And let me tell you why you won't be nervous about this either, why we won't be nervous about this. So first of all, we're not going to see this till chapter 5. So by that time, we're going to be very, very, we're going to spend chapter 1, 2, and 3 only talking about one category, or categories. Okay, we're not going to talk about these fancy categories. Chapter 4 is where we relate one category to another category, and chapter 5 is where we talk about these more souped up categories where you can do more things, where you can combine the elements and combine the morphisms. Okay, and we're going to get there. But again, you shouldn't be nervous about that because we're going to see it in its proper time. Okay. This parallel processing and sequential processing is something that shows up not only in computer science, as you can tell, but also in math and in physics. You have these two different types of processes that work at the same time, and that's an important thing. Okay, so that's my introduction to monoidal categories and why they're very important. Let me just tell you another thing about monoidal categories and why it's a fascinating area. So let's go back and talk about regular numbers. We could talk about x and y and z, okay? And we could talk about different operations on the numbers. For example, x tensor y tensor z. Now, it depends what operation you're doing there. If you're talking about numbers and you're adding numbers, then it's a fact that x plus y plus z, it doesn't matter how you parenthesize them. Okay, you can put the parentheses this way, you can put the parentheses this way, they are equal. Okay, and since they're equal, you might as well leave out the parentheses. That's called associativity. Okay, here's another thing. A plus b is equal to b plus a. Okay? When you add numbers, it doesn't matter which way you do it, what order it is. Now, this is different than, let's talk about subtraction. A minus b minus c, a minus b minus c. Well, this is different than this. Okay? And a minus b is different than b minus a. They're different numbers. Okay? So, when you're talking about regular arithmetic, you have to tell what properties these have. Are they associative? Are they commutative? Are they not associative? Are they not commutative? You have to discuss it. For every single operation, you have to discuss it. Does division work? Does the division not? Etc., etc. Okay? And there's a few more other properties you have to talk about. Well, we're going to have the similar type of questions when we talk about monoidal categories. We're going to have some operation, tensor, okay, and we're going to discuss, hey, is this the same as this? Yes or no? Okay, and we're going to see that there's a lot more variability. And this is called, well, let's just talk about commutativity also, is this combining these two objects in a category? Is this the same as combining these two objects in a category? Sometimes yes, sometimes no. Sometimes they're related, sometimes they're not related. Okay? And so this is about commutativity, this is about associativity, and we're going to see we're going to have a lot more different type of structure, and we have a lot more richer ideas that we can talk about in these different contexts of these different things. Okay? So this over here is called algebra, when we talk about the rules of these operations. Okay? And because these are dealing with categories, and because you have a lot more possibilities here, this is sometimes called higher dimensional algebra. Okay? And it's also sometimes called coherence theory. How does one operation cohere with another operation? Or here we're talking about how does the tensor product cohere with the tensor product. Okay, and so we could talk about something called coherence theory. Now, just like algebra shows up all over in the sciences, in math, and in computers, so too higher dimensional algebra is going to show up all over in these different areas. And this is coherence theory, and this is why this is a central notion. You'll see from chapter 5 on, this idea of coherence theory is central to what we're doing. Okay, so that's called category theory, and that's called monoidal category theory. And before we get to the next video, I just want to say one thing. So while I was writing this book, I was writing a mini course, and one of the mini courses was called Theoretical Computer Science, which is about Turing machines and computability theory and complexity theory and how complicated things are. And I was doing this as a mini course in monoidal category theory. And what happened was this mini course was getting longer and longer and longer, and I was seeing that one could describe more and more of these phenomenon using this. Anyways, the mini course became too big, okay, for the book. I didn't want to spend the whole thing in the book. So what I did was I took it out of the book and I made its own book to it, and it came out a year earlier. It's called Theoretical Computer Science for the Working Category Theorist. That's a joke because the main book in category theory is called Mathematics for the Working Category Theorists. I'm sorry, Categories for the Working Mathematician, which is basically, if you know a lot of mathematics, you can learn category theory from that book. Okay, and so this was saying, look, from the amount of category theory you know from a certain point in this book, you can learn a lot of theoretical computer science. And so this book is 150 pages. It came out from Cambridge. And it's, if you're into theoretical computer science, and you're following these lectures, at some point you will easily be able to pick up a lot about theoretical computer science. Even if you just know you can learn a lot even without knowing theoretical computer science. But it's absolutely amazing how many theorems and ideas can come across using the language of category theory and monoidal categories. Okay, and it's all done in this book. Okay, so let's roll up our sleeves and let's get busy and start with section 1.4, which is or 1.3, which is a big introduction, just talking about sets, functions between sets, operations on sets. This can get simpler than just sets, and so we like talking about sets, and we're going to get a lot of different ideas from that. Okay, that's foreshadowing, and I hope you enjoy. Again, contact me if there's anything, suggestions or comments or criticisms. Let me hear from you. Okay, take care.